Because I'm going to be going back and forth, let me switch this presentation to go entire screen, because I want to discuss the graph. I already plotted the graph, so I want to just discuss it. All right, you see my screen now?
Yes, sir.
Okay, perfect. All right, so now it says here that students carrying out an experiment to demonstrate a random process such as radioactive decay used a large number of dice to represent unstable atoms. The dice were tossed repeatedly, with those throwing 6 discarded after each throw. So what they're doing basically right here, they're doing a simulation or an analogous approach to, well, not necessarily well, they're doing an analogous approach to show that radioactivity, it's a random process, right? So we all know, I mean, play board games, with a dice and we, it's basically a random thing, when you throw a 6 versus when you throw, a 5 or whatever. So it's a random process. So they're using that idea to actually demonstrate that radioactivity is random. All right, so with this question right here, we're given this table, right? And as I said, we have to be comfortable when it comes down to being provided with a table, and then figuring out how to fill out that table in order to move forward. Now, interestingly, this question, even though the table is a part of the question for you to fill out, it's not really needed to plot the graph, and you're going to see why. All right, so let's say first thing we need to do is complete table 1 by inserting the number of dice discarded for throws 4 to 13. So what we're going to realize is that initially we would have started out with 80 dice, right? Then after the first throw, 12 were discarded, right? And the number of dice remaining is just 68. So if you look at these 3 numbers right here, what do you realize? From 80, 12, 68, what do you realize?
Sir, that 12 is the difference of 80 and 68, sir.
Right, so 12 is just the difference of 80 and 68. So that can now help us to actually fill out the table, right? Because if we said that the difference of, what you said, Kiara?
The difference of 80 and 68 is 12.
Difference of 80 and 68 is 12, right? So to find the number of dice discarded, we just subtract the previous number of dice from the current. So in other words, same thing right here. So the previous is 68 and the current is 57. So we subtract these two, we get 11. Similarly, previous is 57, current is 51. We subtract these, we get 6. Everybody seeing that? Everyone seeing that?
Yes, sir.
So to continue,
Yes, sir.
right? So to continue, we will just subtract the current from the previous. So we'll do this subtraction right here. This works out to be what? What's this?
7.
7. Next one.
6.
6. Okay, continue.
7. 6.
Is it like 4?
4.
4, okay. And this is 5. This is 1. This one is 3. 2. Right, is that so? On the right path? Talk to me, we're on the right path? Right path.
Sir.
Alright, so this one would be so what would be the difference of 10 and 8?
2.
Okay. Alright, So that's the table completed, right? Now, notice here it says that using the data in table 1, plot a graph of dice remaining versus throw on the grid paper. So what we require to plot is the number of dice remaining against throw. So realize that the number of dice remaining, all the values were provided. Okay? Sarah?
Yes, sir.
Right? So in this case, I mean,
Yes, sir.
right, so I just wanted you to realize that for this one, we weren't really required to fill out the table in order to plot the graph, right? Because we're plotting dice remaining against number of throws. Cool?
Yes, sir.
Okay. So now, in this case, now we're plotting dice remaining versus throw. So what quantity will be going on the y-axis? What quantity will be going on the x-axis?
Sir, dice remaining will go on the y-axis, zero will go on the x-axis.
All right, so we're going to plot the dice remaining on the y-axis, number of throws on the x-axis. So again, once we're given the statement where we say plot a graph of, in this case, dice remaining versus throw, dice remaining goes on the y-axis and throw goes on the x-axis. So now, as I said, I would have plotted the graph of this just to ensure that, we don't spend a lot of time going over the graph. So let me just switch to the graph. So we're seeing my screen. The screen is still showing.
Yes, sir.
Everybody seeing this? I want to hear from a few persons. Are we still hearing? Still connected? What's going on?
Yes, sir.
Yes, sir.
Okay. So we have the graph right here. So I would have plotted all the values, right? And I would have drawn the smooth curve, right? Now, when you're drawing a smooth curve, especially if it is that, you're given a graph like this, right? You essentially just want to show the general trend, right, of the points. So this is the trend of the points. So you will just simply make a nice smooth curve. Now, you're not required to draw the curve through all the points because chances are it will not go through all the points and give you a smooth curve. So you just want to, as I said, draw a nice, smooth, freehand curve to get this done. So now, any questions on this?
No, sir.
Okay, all right. So now, let's see what next they say we need to do. So let's say we're to use the graph to determine an average value for the half-life of the process. By the way, when we talk about half-life, what's the half-life? What do we mean by half-life?
So the time it takes for radioactive substance to decay in half.
Okay, the time for a radioactive substance to decay in half. Now, what about the radioactive substance is going to, and I'm going to just make an adjustment, what about the radioactive substance will reduce by half?
The mass.
Mass, right? Or
Activity.
right, or its activity, right? So even though it's not required right here, I'm just going to write a definition for the half-life. So the half-life of a radioactive substance is the time taken for its activity or mass to reduce to a half of its previous value. Alright, so that's the half-life. So we must be familiar with this definition as we're going into the exam. Alright, so anybody have any question? Was any question? Demario? Question? Pretty straightforward or what? You good? Alright. Alright, so let's go to the graph now to see if we can determine the half-life. So with the graph right here, right, in order to find the half-life, we can consider the time it takes for, in this case, the number of dice remaining to reduce to a half of its previous value. So how we can do that is we can say, okay, the initial number of dice is 80, right? Now we need to know the time now it's going to take to go from 80 dice to half of 80. What's half of 80?
Sir, 40.
40, right? So what we simply do is we go to 40, with a broken line, go to the graph like this, and once we're finding the half-life and we're doing this, we have to show it on our graph. So we go like this, right, go straight down, because the examiner will want you to show this, right? So when the number of dice was at 80, the time was 0, right? When the number of dice is 40, the time is, this is 4.1 from my graph. So therefore now, we could say that our first half-life will simply be equal to the time when the number of dice is 40 minus the time when the number of dice was 80. So we say this is going to be 4.2 minus 0. So I will say 4.2 minus 0 is just going to give me 4.2 throws. So let's just say 4.2, right, like that. Everybody with me so far? Come on.
Yes, sir.
Are you following? Following what's going on?
Yes, sir.
Okay. All right. So what we do next is we can say, okay, we can determine a second value for the half-life. So let us say we consider that the number of dice is at 40. So we take half of 40, which is 20. The same process, same procedure. All right, go straight across. All right, and straight down. All right, straight down. All right, so now we do the same thing now. So when the number of dice was at 40, it was 4.2. Right now it's at 8. So our second half-life now, we're going to say 8 minus 4.2, and this would work out to be what? Okay, so we get 3.8, right? Now, once we have two values, we can find the average. I mean, we could go and obtain a third value, right? And all we will do is we'll just find half of 20, which is 10, and find the time, and then do our subtraction also. But since we have these two, let us say we just find the average of these. So the average half-life, right, will be equal to the sum of these, so 4.2 plus 3.8, and we divide by the number of values, which is 2. So this works out to be what? Right? 4. right? So the average half-life is going to be 4. Now, typically, when you're given a question like this, you will oftentimes be given the time, so you will have a unit of time in this case, right? So in this case, we say 4, right? Let us say we had measured time right here in hours. All we would say is that the average half-life would be 4 hours like that. Okay? Any question? Any question? Any question?
No, sir.
Okay. Philip, any question from you?
No, sir.
All right. Clear? It's clear? Is it clear?
Yes, sir.
All right, cool. So, so that's that. Now let's go back to the screen. I'm gonna switch this thing. All right. So once you have done that, next question now says now that how many half-lives would it take for a sample of carbon-14 to reduce to 1/32 of its original mass? So how we do this? How we do this thing? How do we do this? Anybody know?
So do you say 14 times the 1 over 32?
Okay, 14 times 1 over 32. Well, not quite. Anybody else have any suggestion? Yes or no? Speak to me. Any suggestion?
Chapter 6, Step 4.
Okay. Yes, will do. So, I was saying about this question. Anybody? Or we're gonna work this question.
Sir, question D.
Yes, question D.
Sir, I multiplied halves by halves until I got 32 halves. Sir.
Repeat that for me.
Sir, I multiplied halves until I got 32. 1
Oh,
over 32 halves.
okay,
1
okay.
over 32, sir.
1/32, okay. And how many times did you have to do that?
Sir, 5 times.
5 times. Okay, cool. So, how many half-lives will it take?
Sir, 5 half
5
lives.
half-lives. Okay. Well, that's an interesting way to look at it. But let's just discuss it. So, for this one now, what we're going to consider that, okay, initially the mass, let us say initially the mass is going to be 1. Okay. So initially the mass is going to be 1. So now, after 1 half-life, what's going to be the mass?
0.5.
0.5, right? Or a half. Let's do it as a fraction. So we can use arrows to show the half-life, the decay, right? So after 1 half-life, we use an arrow to show us that it's going to reduce from 1 to a half. Then after another half-life, it's going to go to
A quarter.
a quarter, right? And we're trying to find 1 over 32. So we're going to continue, right? So we get 1 over what?
8.
8. And then
1 over 16.
1 over 16. And then? And
1 over 32.
1 over 32, right? So the arrows right here shows up the half-life decay process. So this is our first half-life, second half-life, third half-life, fourth, fifth, right? So it's going to take 5 half-life periods for the sample to reduce up to 1/32 of its original mass. So we could say that's going to take 5 half, HALF, half lives. Cool?
Yes, sir. Sir, you could just go into problem.
So what we're saying is that we want to know how many half-lives would it take for a sample of carbon-14 to be reduced to 1/32 of its original mass. So what we can consider is we can consider that, okay, initially it's gonna be 1, right? So we'll consider it to be initially at 1, and we just simply consider that after each half-life it's going to reduce to a half. So we're going to have 1 half of 1 is just 1 over 2. Half of a half is 1 over 4, or a quarter. Then half of a quarter is 1 over 8, right? Continuing down until we get 1 over 32. Now also, if you realize that each time, because I mean we can look at it this way. We can look at it this way. Let's say initially it is at 1, so that's 1 over 1, right? And what you do is just double the denominator each time. So we have 1 right here, we double it to 2, double it to 4, double it to 8, double it to 16, and double it to 32. And we just, as I said, show our arrows to show the decay. Okay?
Oh, okay.
So that makes sense to everybody?
Yes, sir.
Alright, so it's half-life, 5 half-lives. As I said, I mean, Kara, your method, you know, is you know, I mean, definitely an interesting way to look at it.
Sir, it's almost the same as this, sir. It's just that I had to multiply to get my answer, sir.
Right.
I just did the working out.
Okay. Alright. Anybody else got the answer for this?
Sir, I got the answer.
Okay, okay, good. And I remember you said something about or you multiplied you said that you multiplied what, 14?
Right. Yes, sir. Sir, and then sir, and then I did a half like 14 divided by 2 and blah 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 until I got the number.
Okay.
So you can understand.
Well, I'm so you said you multiplied 14 by 1 over 32.
Yes, sir. To get like what would be the half life? What would be what would be?
The mass.
Yes, sir.
Uh-huh.
And then I started to do the half life of course like 14 divided by 2 like in the 7 and then 3.5 until I
Oh,
got
okay.
the number.
Okay, I see what you're saying.
Yeah.
Okay. So that's another way to do it because I mean you could look at it from a perspective of any number really, right? You can look at it at any number. So I mean that's a good way to look at it. So let us say we say that initially the mass is 100, right? Now we could find what is 1 over 32 of 100 by just simply dividing 100 by 32 and you're going to get some decimal value, right? Then you're going to say, no, okay, if you divide the original number by 2, continuing, how long will it take you to get down to the decimal value when you divide 100 by 32? So that's another way to look at it. And as I said, I mean, I see you guys, applying yourselves with this question, to actually figure it out. But this is the most, what can I say, I want to say straightforward, but maybe your method is straightforward. This is the most straightforward way to look at it. All right? Agree? Quickly? Agree?
Yes, sir.
Okay, perfect. So now, next now they say that given that carbon 14 has a half-life of 5,700 years, determine how long it would take for this reduction to occur. So what do we do for this?
What I did, I said, since one half life equal 5,700 years, 5 half life equal x, and I cross multiplied and I said x equal 5,700 times 5, x equal 28,500 years.
Exactly. Good, right? So therefore, now the time now will simply be equal to, because remember, since the decay took place over 5 half-lives, as we said right here, and each half-life is 5,700 years, all we have to do is just multiply the number of half-lives by the half-life. So it's 5,700, right, years, right? And we get, this is what now, what you got when you multiply this?
So when you say 8,500 years.
Years, right? So that's good. But do you have any question on this?
No, sir.
Okay. All right. So this one now says that carbon dating involves the use of carbon 14 to determine the age of ancient objects. Explain how this is accomplished. All right. So let me just run through the discussion and then we can probably put it down on paper. So when living organisms are, well, this can probably sound a bit redundant. When living organisms are alive, which, as I said, a bit redundant, but when organisms are alive, right? Because for instance, I mean, yes, when organisms are alive, for instance, plants, yeah, in a sense, they use carbon dioxide as a raw material in the process of what?
Photosynthesis.
Right, photosynthesis, right? So they will use carbon dioxide in photosynthesis in order to make food, right? Now, some of that carbon dioxide that they take in contains radioactive carbon 14, right? So some of that carbon dioxide, as I said, it contains radioactive carbon 14. Now, what's going to happen is that while the plant is alive, right, the amount of radioactive carbon in its system will remain constant because every day the amount of radioactive carbon, you know, is being replenished. Make sense? No? Yes? Huh?
Can you please repeat that, sorry?
Yes, so I'm saying that when a plant is alive, it takes in carbon dioxide, you know, to carry out photosynthesis. But what I'm saying is that a portion of that carbon dioxide, contains radioactive carbon-14. Now, while the plant is alive, it's going to constantly be replenishing the amount of carbon-14 that is in its structure. Yes?
Yes, sir.
Now, when that plant dies, it's not going to be taking in any more carbon dioxide. So what you're going to see now is that the amount of radioactive carbon-14 is going to start to deplete. Cool?
Yes, sir.
Now, what scientists would have done is that they would basically, estimate the amount of radioactive carbon-14 that the plant is expected to have during its lifetime or while it is alive. Now, what they will do now is that they will now measure typically the activity, right? They'll measure the activity of the radioactive carbon-14 in the plant, right? And then they'll be able to know basically be able to determine the age of that plant. So in other words, what they do, think of it this way. So let us say the amount of radioactive carbon in the plant while it is alive is, let us say it is at 10, right? Now, after they examine the plant, they realize that the amount of radioactive carbon in the plant is 5. So when it was alive, it was at 10. When it is dead and they are examining it, it comes down to 5. Okay? Yes?
Yes, sir.
So the amount of radioactive carbon, it reduced from 10 to 5. Now, 5 is what fraction of 10? A half, right? So it simply means, you know, that the amount of radioactive carbon would have reduced by a half. Yes?
Yes, sir.
So how long would you say that plant would have been dead? If the half-life of carbon-14, as we say right here, is 5,700 years.
Sir, would it be a half of that time?
No, no. The time will be this, you know, because again, remember, the half-life is the time it takes to reduce by a half. So since it goes from 10 to 5, that will take one half-life for it to go from 10 to 5. Make sense?
Yes, sir.
And one half-life is 5,700 years. So therefore, it simply means that the plant would have been dead for 5,700 years. Make sense?
Yes, sir.
Anybody have any question? Anybody have any question? Yes, no?
No, sir.
Philip?
No, sir, don't have any questions.
Okay. All right. So what we but anyways, so what we say for this now is that the amount of radioactive carbon 14 in living organisms remain constant, right? Now, after death, the amount of carbon-14, right, reduces. Let's write it like this. amount of carbon-14 reduces, right, over time, right? Now, after a certain time, the amount of carbon-14 present can be determined, right? And by considering the half-life of carbon-14, the age of the artifact or the plant or dead organism. So let's say the age of the, let's say, material can be determined. Right? So we have to mention the fact that, okay, the activity or the amount of radioactive substance while the organism is alive is going to remain constant. But once it is dead, it's going to start to reduce. Right? And then you're able to know to measure, okay, what is the amount of radioactive material remaining, and then you can now determine the age of that plant by looking at the half-life. Continuing on. So next thing now says we're to define the term linear momentum. So what we say about linear momentum?
Is the product of mass and velocity of energy.
Right, so this is the product of mass and the velocity of an object. So therefore, the SI unit of linear momentum would be
kg/ms to the minus 1.
right, so kilogram, this is too dull. So we will have kilogram meters per second to the minus 1, or we can write it as kilogram meters per second. Okay? Body good? Is everyone okay?
Yes, sir.
Okay. Now state the law of conservation of linear momentum.
The principle of conservation of linear momentum states that if two objects collide, then the total momentum before and after the collision will be the same if there is no external forces acting on it.
Right, good. Right? So, as I mentioned, if two objects are colliding, or if two objects should collide, right, their total momentum before will be equal to their total momentum after. And this is only if, as you mentioned, no external forces are acting. Right? So we can put that together and we can say
Yeah, I
that.
have this one.
Yes, go ahead.
Oh, it states that for an enclosed isolated system, the total momentum of the system before collision is equal to the total momentum of the system after collision.
Very good, right? So that mention of a closed system just simply tells us that there are no external forces because the collision is actually isolated from any external influence. So we can say that for an isolated system, right, the total momentum before is equal to the total momentum right? We could say that system of colliding objects right? Colliding objects. Total momentum before collision, because typically when we're looking at momentum, we're gonna be most times be considering collisions. Before collision equal to the total momentum after collision, right? But in terms of this law of conservation of linear momentum, it works for collisions and also for explosions, right? But as I said, typically we're going to be dealing with collisions, okay? But you have this. All right, so Demario, yes, repeat. Okay, Demario,
Sir?
yes, are you okay with this?
Yes.
All right, so let's continue. Let's continue. So next one now says we're to state two real life examples that demonstrate the law of conservation of linear momentum. So what can we say about this?
So I have a bullet being fired from a gun, and I tell this while hitting an arcade.
Right? So a bullet being fired from a gun. How does that demonstrate the law of conservation of linear momentum? Huh?
Sir, can you repeat?
Yes. How does a bullet being fired from the gun demonstrates the law of conservation of linear momentum?
Sir, when after the gun fires, sir, then the bullet would have gained velocity to its to the right, sir. So because of that, the bullet now has momentum to the right, and because before there was no momentum in the system, sir, because before there was no momentum before the gun was fired, then there will be zero momentum now because if the gun has an equal momentum and opposite to it, then that will mean that the momentum of the gun and the bullet is equal, which proves the law of conservation of linear momentum. So I'm not sure if I explained that correctly.
Perfect explanation. So as I mentioned, initially, the gun and the bullet inside the gun will have zero momentum, but the bullet is gonna go to the right and it's gonna have a momentum, mv, right? Let's say mv let's say m1v1, right? As a momentum m1v1 to the right. While at the same time now the gun, what usually happens to the gun when a bullet is fired from it?
So it revolves.
Well, it recoils.
Sorry, like
It recoils.
recoils.
Right. So it moves to the back or move in the opposite direction to the bullet. So the gun at the same time is gonna move in opposite direction with a momentum m2v2. Now what we're saying now is that this momentum and this momentum will both be equal, right? So because these two momentum are equal and they act in the opposite direction, we will subtract. When we subtract two identical values, we're going to get 0. So it proves to us that the total momentum before, right, which was 0, is also equal to the total momentum after. So we could say a bullet fired from a gun moves forward with the same momentum as the recoiling of the gun. Okay, and you had mentioned another example. What was that?
Sir, when a tennis ball hits against a tennis racket.
What usually happens?
Sir, the force that sir, you have to give me a second to
Think about it. All right. So in the meantime, let me share one example. So think about, having two identical balls, two identical steel balls, right? Let us say A and B, two identical steel balls. Now, if it is that, let us say steel ball B is stationary. If you launch ball A at a certain velocity, let us say 2 meters per second towards ball B, and they collide, what you're going to see is that after the collision, ball B will move off, right? Ball B will move off with a certain velocity. So again, ball A collided with the stationary ball, and again, they're two identical balls. So ball A collides with ball B with a velocity of 2 meters per second. Now after the collision, now ball B is going to move off. What's going to be the velocity that ball B will move off with?
I don't know, 0.
You cannot move off with 0. It's moving. So it will have a velocity. Huh? Because, huh? What are we saying? Alright, so again, let me put in some numbers. So we're saying that these are two identical balls. So they have the same mass, right? This one has a velocity of 0 meters per second. This one has a velocity of 2 meters per second. That is before they collide. Now what I'm saying is that after they collide, right? Let us say ball A remains stationary after the collision. If ball A remains stationary after the collision, ball B will move off. And it's going to move off with what velocity?
The initial velocity of ball A.
Right, it's going to move off with the velocity of ball A, which is initial velocity of ball A, which is 2 meters per second. So we could say that two identical balls colliding. If, let us say, first ball, or let's say ball A has a velocity of 2 meters per second, ball B will move off with a velocity of 2 meters per second, while ball A remains stationary. This is making sense? Huh? Michaela, this making sense?
Yes, sir.
Okay. Any questions so far, Michaela? Okay. All right. So next one now says that trolley A and trolley B collided head on. Trolley A of mass 72 kg was moving towards the west at 5.5 meters per second. Trolley B of mass 69.4 kg was moving towards the east at 4.5 meters per second. And then so we need to calculate the initial momentum of trolley A. So to do this, we're going to use our formula, which will say that momentum P is equal to the mass multiplied by the velocity. So the mass of trolley A is 72 kilograms, so 72 kilograms multiplied by its velocity, which is 5.5 meters per second. So this works out to be what?
396 kilograms meters per second.
Kilograms meters per second. All right. The initial momentum of B now, so we'll do the same thing. Say that momentum P is mass times velocity. The mass of B was what?
Sir, it was 69.4.
Kilograms. And the mass of, and the velocity?
Was 4.50.
Okay, so sorry about that. Right. So what was the velocity again?
Sir, 4.50.
Right, 4.5 meters per second. And after multiplication, what do we get?
312.3 kilometers per second.
Kilometers per second?
Kilograms per second.
Right.
Kilograms meters per second.
So 312, there was a decimal?
Yes, sir, 0.3.
0.3 kilogram meters per second. Next thing now, it says that assuming the trolleys locked during the collision and that they moved off together in one direction, determine the speed and the direction of the joined trolleys immediately after the collision. So this question is related to the law of conservation of linear momentum, right? Because what we're going to have to consider in this case, we're going to have to consider that, okay, we're going to have to consider.
The collision because the movement of together.
Okay, good, right? So we know, can identify the type of collision. So we're saying that it's an inelastic collision. So we know that it's an inelastic collision because they move off together, right? Once it is inelastic, they move off together with a common velocity. Right. So now, what we're going to say is that the total momentum before, right, total momentum after. Now, since it is an inelastic collision, we can write that the total momentum before will simply be m1 u1 plus m2 u2, which is equal now to m1 plus m2, right, multiplied by the common velocity. So now, once you have this right now in this case now, we have to just be a little cautious in terms of how we go about working this question, right? Now, notice that they say that they collided head-on, right? And also they would have said that, okay, one was going to the west, one was going to the east. So what does that tell you?
Change in direction, so it will be a negative.
Let's just be clear. We want to know the relative movement of the two trolleys. So what it says? It says that they collided head-on, right? In order for them to collide head-on, what must be their relative motion in terms of a direction? In other words, what would be their relative direction to each other in order for them to collide head on?
From east to west.
Huh? Alright, so again, consider the situation. If the two trolleys are colliding head on, right, what must be their relative direction?
They must be going in the opposite direction.
Right, they must be going in the opposite direction, right? Because notice they said that one was going to the west, one was going to the east. So they're moving in opposite direction, so they are able to collide head on. Now, in this case, we have to remind ourselves that we're dealing with vector quantities, right? We're dealing with vector quantities. Now, this value represents the momentum of trolley A before collision, let us say. And this represents the momentum of trolley B before the collision. Now again, we're dealing with vectors. So one is going this way, one is going this way, one is going that way. Now once we have vectors in opposite direction, we can just right away think that, okay, we will have to subtract the magnitude. Everybody with me? Yes, no? Maybe so?
Yes, sir.
Right?
Yes, sir.
Philip?
Yes, sir. Yes, I
Yes.
get what you're saying, sir.
All right. Cover on. So we're going to say that the, what's this again now? The momentum of trolley A, let us say that is 396. So we're going to say 396 kilogram meters per second, because we just multiply M1, U1. We already did that already, so we're not going to repeat doing that. Then now, as I said, because they're going in the opposite direction, even though we say plus right here, we still want to know the total momentum. And we can actually prove how we're going to get the minus by considering that, okay, the velocity is going to be acting in the opposite direction, so we can use a negative sign. Then we're going to end up with negative being right here. So we end up have to subtract. So we say minus the momentum of this one, which is 312.3. Let me know if everybody comfortable with this. Everybody comfortable with this? Everybody comfortable with this? Speak to me.
Yes, sir.
All right.
Yes, sir.
Okay. So now that now is equal now to the mass of trolley A. Remind me of the mass of trolley A.
72.0 kilo.
72.02 kilogram. And trolley 2, I mean, yes, mass trolley B.
69.4
kilogram, right? And we multiply that by V. So now we simplify the left hand side, right, with a calculator. What would we get? If we say 396 minus 312.3, that's how we go. All right, what do we get? All right, so 83.7 kilogram meters per second is equal to, we'll add these together, what do we get? Okay, so 141.4, this is kilogram, and we multiply it by the velocity v right here. Then now, all we simply do is we divide both sides by 141.4 kilogram, 141.4 kilogram, and we see that v then now is going to be what value?
0.59 meters per second.
Right? 0.59 meters per second. Right? But I agree with this. So we get 0.59 meters per second. Huh?
Yes.
Now, let's say that we need to also tell the direction. So we're going to tell the direction. Huh?
You see it going from east to west. So
But how we gonna justify that? How we gonna justify that? Because we must be able to justify the information. Huh? Huh? How we gonna just?
So I'm not sure if it's right, sir, but I would say we're going from east to west because the initial momentum of Charlie A was larger than the initial momentum of
Yes,
Charlie B.
that's exactly correct, right? So because the momentum of Charlie A was larger and Charlie A was moving to the west, right? That's what you were saying, Sarah,
Yes, sir.
right? So Charlie A was moving to the west and its momentum is larger, right? So the wreck, which is the two cars locking together and moving off, they're going to move in the direction of the larger momentum, right? Also, if we had said that, okay, Charlie A was going to the, so if we had said that, okay, west is positive and east is negative, because we get a positive value for our answer, it simply means that the wreck will be going to the west, which is the positive direction. But as Sarah says, we can consider that, okay, since the momentum of Charlie A was larger, after the collision, both vehicles will move in the direction of Charlie A, which is to the west. Cool?
Yes, sir.
All right. So now, next one now, let's see what's here. So this one says that we're to explain what is meant by a transverse wave.
these are waves in which the particle of the medium oscillate perpendicularly to the direction of the energy transfer.
All right. So these are waves in which the particles of the medium, what do you say they do?
Oscillate perpendicularly to the direction of the energy transfer.
Right. Perpendicularly to the direction of the energy transfer. Right? And they say they want one example of transverse wave. So what we can say for this one?
Water waves.
Okay, water waves. Any other example? Any other example?
So the electromagnetic waves could also be an example of transverse.
Absolutely.
Radio waves.
Right, electromagnetic waves, which is an example is radio waves. So all electromagnetic waves are electromagnetic. Okay? Now, says here to define ultrasound. So what's an ultrasound?
This is a sound of vibration having an ultrasonic frequency.
Okay, but that still don't allow me to understand it. What do you mean by ultrasonic frequency? What are we talking about?
So it has to do with sound.
Yes, that's why they say ultrasound. Right? What's an ultrasound?
Sorry, I have this is a song.
Yes, go ahead, Kara.
This is a sound wave with a frequency greater than 20,000 hertz.
Okay, good. Any other definition?
That it's a high frequency sound wave.
High frequency sound wave. Yes, it's a high frequency sound wave, but you want to be a little more specific, right? Because high is a relative term, right? Now, as Kiara would have mentioned, ultrasounds, we can say that this is a sound wave having a frequency above the frequency, or let's say the range of frequencies, above the range of frequencies detectable by the human ear, right? And human beings can detect frequencies from 20 hertz to what?
20 kilohertz.
Right, 20 kilohertz. Right? So as I mentioned, Kara, that it is above 20 kilohertz, so it's ultrasound. Okay? Yes?
Yes, sir.
Right?
Yes, sir.
Next one says now we have to state one example of the application of ultrasound. So what do we say for this?
Sir, examination of a fetus.
Right? So to examine the fetus, F-O-E-T-U-S, of examine fetus in pregnant mothers. Right? Let's say that. In pregnant mothers. Any other thing we can use it for?
Let's use it for echolocation.
Right, yeah. So used in some animals, so used by animals such as bats, by bats for echolocation. Another application? Another application? By ships to detect the depth of the seafloor, right? Or even to detect the depth of objects submerged beneath the surface. All right, so these are three applications that we can think of. Okay? Talk to me again.
Yes, sir.
Okay. So now, next one now says that a slinky spring can be used to generate a transverse waveform. In the box below, draw and label this waveform, clearly identifying particle movement, waveform movement, and at least one crest and trough. So for this one, what they want us to do, they just want us to draw the waveform of a transverse wave. So we could go like this, right? And the waveform of a transverse wave will look something like this, right? Let's say this, right? So with a transverse wave, as we would have mentioned, that the oscillations are perpendicular to the direction of the energy transfer. So therefore now, what can we say about the particle movement in this case? How will the particles be moving in this case?
Repeat.
We want to show the particle movement of this transverse wave form that we're showcasing right here.
Sure, sir, will you just draw an arrow?
Huh?
An arrow east.
Going where?
East.
Right, but again, we want to show the particle movement, right? How will the particles be moving for us to get the transverse wave?
Perpendicular.
Perpendicular. Right, to the wave, right? So in which direction would the wave be traveling though? Let's see if we can get that first. wave is going to be going up and down?
To the right.
Right, the wave is going to be going to the right. So the waveform movement will be going to the right. So waveform movement is to the right. So if the wave is going to the right, the particles are going to be going how?
Left.
Perpendicular, we said, you know.
To the right too?
Perpendicular. Perpendicular. What does perpendicular mean?
So just draw like on the y-axis right this.
Where? Alright, before we talk about drawing any arrows, let's just agree in terms of the particle movement. How will the particles be moving? Is it perpendicular or perpendicular?
Perpendicular.
Right, perpendicular, right? So if our wave is going to the right, the particles must be oscillating perpendicular. So in other words, they're going to be going up, right, as well as down. So this is going to be our particle movement. This makes sense?
So you're gonna let me take it afterwards?
Yes, absolutely. So the particle movement will be up and down, and the waveform will be going to the right. So we get that perpendicular relationship between the waveform movement, which is the energy, and the particle movement. And that's why we need to show one crest and one trough. So we're going to have our crest right here. Right? And let's say we call this one our trough. All right? Everybody pleased with this?
Yes, sir.
Okay. And it's hearing from persons like Demario, Cavon, what's happening? Irelanders.
Sir?
Is you guys still yes, yes, Cavon, what are you saying?
You can repeat?
You're not paying attention? Why you want me to repeat?
Oh no, I just didn't hear what you said.
So you were paying attention?
Oh yes, sir.
I asked if you are following what we're doing right here. Because I was saying I'm not hearing from you and others.
Yes, sir, I'm following.
Okay. Demario?
Yes, sir.
You're following Demario?
Yes, sir.
Any question?
No, sir.
Okay. Alright, so we can move. Somebody say yes?
Yes,
Yes,
sir.
sir.
Okay. Alright. So next one now says that a steel pan produces a sound of frequency 0.35 kilohertz. The speed of sound in air is 340 meters per second. What is the wavelength of the sound generated by the pan? How would we do this?
You have to use the formula V is equals to F by lambda.
F by lambda, right? And we're trying to find the wavelength, right? So we make wavelength the wavelength the subject, which is lambda. So we're gonna get the wavelength lambda is equal to
F times V.
F times V. We agree?
Times F. Yes, sir.
What would it be? We agree?
Yes, sir.
Okay, everybody agree?
Yes, sir.
Yes, sir.
All right. So before we confirm or before we move forward, let's consider.
So,
Yes.
one thing, frequency is supposed to be in hertz, so you have to convert.
Yes, but let's solidify the formula first. So we have V is equal to F lambda. Our objective is to make lambda the subject. So we need to have lambda by itself. Now we have F times lambda. So what we can do is we can divide here by F. So we cancel this one. And we have lambda by itself. But anything we do on one side, we have to do it to the other side. So we get lambda is equal to
V divided by H.
right? V divided by F. Now, we can now go to do our calculation. But as I mentioned, so first of all, the velocity or the speed of the sound V is 340 meters per second, and the frequency F is 0.35 kilohertz. Now we can convert from kilohertz to hertz by doing what?
Divided by 1,000.
We're going from kilo, which is large, to hertz, which is small. So we're going to multiply. So large to small, we multiply. So multiply by 1,000. We go 1, 2, 3. So we get 350 hertz. So therefore now, V is 340 meters per second divided by 350 hertz. And this is
0.97 meters.
meters. Okay? 0.97 meters. Next thing now says that if the sound is generated underwater instead, what is the frequency that would be detected? What are we going to say for this? What could we say for this?
Can I explain it for me?
Yes, definitely. Right? So they're saying that if the sound is generated underwater, instead, what would be the frequency? So what would we say for this?
So it's asking for the actual frequency, sir.
Yes.
So would it be 10 hertz to, sir, greater than 10 hertz, sir?
Greater than 10 hertz. Yes, can be greater than 10 hertz, definitely. But let's just kind of because this question is more of an analysis question in terms of analyzing the situation. So what they're saying is that the sound is generated underwater, and we want to know, okay, what's going to be the frequency. Now, what we need to be aware of is that when we have a particular wave, right, from a source, in this case, the source would be the steel pan, right? The source would be the steel pan. Now, the steel pan, it produces sound of this frequency, right? So the frequency is set. So now, what we're going to see now is that regardless of the medium that the sound travels through, the frequency will always remain the same. But you can agree to that?
Sir, you can repeat what you said, please?
Yes, I'm saying when a wave is produced from a source, its frequency is always fixed, right? Its frequency is fixed. Now, regardless of the medium that the wave is propagating through or traveling through, its frequency will be unaffected. Okay?
Yes, sir.
Right? So the frequency is essentially a set parameter of the wave. Right? What can change is the speed of the wave or its wavelength. So if the speed decreases, the wavelength will also decrease. Okay? Yes?
Yes, sir.
Right? And that ensures that the frequency remains the same. So in this case now, what we could say now is that the frequency, right? So the frequency, F, will still be the 350 hertz. Cool?
Okay, sir.
Yes, sir. Sir, would be incorrect if you wrote 0.35 kilohertz.
kilohertz.
No, same thing. Same thing. All right? 0.35 kilohertz, same thing. All right? Next one now. So number 4 says that on figure 4 below, sketch the graph of pressure versus temperature in degrees Celsius. So let me just put in Y, X. So this is temperature, let's say in degrees Celsius. And this is what? Pressure. So let's say pressure is measured in pascals. So how would we expect the graph to look for pressure against temperature in degrees Celsius?
So it's going to like go to the negative x-axis.
It's going to go to a negative x-axis, okay? And in order for it
And
to...
a curve.
No, it's not going to be a curve. It's going to be a straight line. No, in order for it to go to a negative...
Straight line.
Hold on a second. It's not, in order for it to go to the negative x-axis, sir, how would we be able to achieve that? What would have to happen? Any ideas?
So like how we're going to like draw it to the negative x-axis.
Yes, how are we going to be able to draw it? What must happen?
So you have to extend the x line
Okay.
to the west.
Right, okay. But
Is that
before we get there though, I mean, we will have to draw the graph, right? We'll have to draw the graph. Hold on a second. All right. Yes. So, right. So I'm saying that first we would have to draw the graph, right? We would have to actually draw the, or in this case, sketch the graph of pressure versus temperature. Now, what we have to be aware of, right? So we're talking about pressure and temperature, right? Which of the gas laws deals with pressure and temperature?
Charles.
No?
Where's the?
No?
so the pressure law?
Pressure law, right? So the pressure law. And what does the pressure law say?
So the pressure law says that for a fixed mass of gas, the pressure is directly proportional to the Kelvin temperature.
Right, pressure is directly proportional to the Kelvin temperature, right? But in this case now we have pressure and we could say Celsius temperature, right? Or temperature in Celsius. So what does Boyle's law say about pressure versus Celsius versus temperature in Celsius? Do we know anything about that?
They're boiled.
Huh?
Boil.
I don't
So
hear.
did you just say boils?
No, I said pressure. What did pressure law say about the pressure and the temperature? In Celsius. Do we know anything about that? Yes, no? Any ideas? Yes, no? Huh? Are we still here? Everybody still connected? Or just me alone here?
Yes, sir. Sir, what was the question again?
The question is, do we know anything about the relationship between pressure and temperature in Celsius?
I don't remember. Sir.
Okay. All right. So pressure is directly proportional to temperature in Kelvin. However, for temperature in Celsius, they are proportional to each other, right? Not directly proportional, but instead proportional. So therefore now, if the pressure is proportional to the temperature in Celsius, when we draw our graph, what we're going to see is that our graph is going to cut the y-axis, right? So that's the only way we can actually get a negative value for the temperature. So now, in terms of this case, but in this case now, what we're going to have is we're going to have our graph looking something like this, right? When we plot pressure against temperature in degrees Celsius, okay?
Yes, sir.
All right, so any question?
So why did George put that on? Why can't it be up like that?
Because they're proportional, right? They're proportional to each other, right? They're proportional to each other. So we will not get our graph cutting the, or not cutting, we will not get our graph passing through the origin.
So if it was passing through urgency, that would that be Charles' law with the volume is proportional to the
No,
temperature?
hold on. Before we talk about any specific law, what we need to appreciate is we're
Sorry.
talking about proportionality, and we're talking about direct proportionality, right? When two quantities are proportional to each other and we plot a graph, we'll get a graph looking like this. If they are directly proportional now, we're going to get a graph looking like this. But because pressure and temperature in Celsius are not directly proportional, they are instead proportional to each other, so we have to get a graph that cuts the y-axis. Cool?
Yes, sir.
Yes, sir.
Right? So that's what we're going to get, right? Anybody have any questions on this? No question? Talk to me.
No, sir.
Okay?
No, sir.
Alright, so now it says now to explain how the graph could be used to derive the Kelvin scale. So Sarah was kind of hinting at it. In order for us to use this graph to obtain the Kelvin scale, what we'll have to do is we'll have to extend our x-axis like this, right? And then what we do now is we will extrapolate, right? Extrapolate, right? To when the pressure is 0. And what we're going to see now is that we're going to get a corresponding value, right, for the temperature, right? And it's going to match up to minus 273 degrees Celsius. Okay?
Oh, so it will be plus again.
Because it's beyond the 0. Remember 0 is right here, so to the left is going to be negative. Okay? Shanice?
Yes, sir.
Right? So that's how we could go about doing this. As I said, what we do is we extend our graph, right, towards the x-axis, and we simply read off the corresponding temperature. Now, this temperature right here is when the pressure is 0. So when the pressure is 0, what that corresponds to? That corresponds to the lowest possible temperature, right? The lowest possible temperature is 0 Kelvin. So this will correspond to 0 Kelvin. So from that now, we can now be able to derive our Kelvin scale. Okay? Cool?
Yes, sir.
Okay? So now, continuing down,
Yes, sir.
it says that using T to represent the Kelvin temperature and theta to represent the Celsius temperature, state the mathematical relationship between the Kelvin and the Celsius temperature scales. So what can we say for this?
Says it T equals theta plus 273.
Right? Theta plus 273. So to convert from Celsius to Kelvin, we just simply add 273. So we get T is equal to theta plus 273. But have questions? Anyone has questions?
No, sir.
Okay. All right. So moving on, says that a container stores 5 cubic meters of gas at a pressure of 13 atmospheres and a temperature of minus 23 degrees Celsius. Calculate the volume that the same gas would occupy at a temperature of 27 degrees Celsius and atmospheric pressure of 1 atmosphere. So let's just kind of zone in terms of what we have. So we're given the volume of the gas, we're given its pressure, right? And we're given its temperature, right? They want us to calculate the volume of the gas if the temperature was 27 degrees Celsius and the pressure was 1 atmosphere. Okay? Seeing this?
Yes, sir.
So what's the mode of attack for this question?
Sir, I used P1 V1 over T1 equal P2 V2 over T2.
Okay. So which equation is that?
Sir, the general gas law.
Right, general gas equation, right? So we have P1 V1. Everybody following so far? Everybody following this? Yes, no, speak with me. All right. So
Yes, sir.
right, so let's say this is V1 right here. This is going to be P1. This is going to be T1, right? V2 is unknown. T2 is this value right here, and P2 is that value. And they say we're trying to find what? V2. So let's rearrange this to make V2 the subject. So upon rearranging this equation, right, what we will do is we'll cross multiply. So let's do the cross multiplication. So cross multiply here. So we're going to get P1 V1 times T2 is equal to P2 V2 times T1. Now we're trying to find V2, so let us divide here by P2 T1, divide here by P2 T1. So then, if we do that, we're going to get that V2 is going to be equal to P1 V1 T2 over P2 T1. Body follow that?
Yes, sir.
So V2 then now is equal to P1. P1 was 13 atmospheres, so we can use 13 atmospheres, right? 13 atmospheres, right? Multiplied by V1. V1 is 5 cubic meters, right? And T2 is what? What's T2? 27 degrees Celsius?
Sir, you said this is Kelvin?
Yes, I have to convert to Kelvin, right? So we're going to convert 27 degrees Celsius to Kelvin.
And then so 27 plus the 273 equals 300.
Right, so T2 then now is 27 plus 273, which is 300 Kelvin, you said?
Yes, sir.
So we have 300 Kelvin. Then now we divide that by P2, which is 1 atmosphere, so we could say 1 atmosphere, multiplied by T1, which is minus 23 degrees Celsius. So we add 273, so we say T1 is minus 23 plus 273, and that's like what? Like 250 or so?
Yes, sir. 250.
Yes, sir.
Right, 250 Kelvin. So we have 250 Kelvin. So now, what we get for this?
Sir, 78 meters cubed.
78 meters cube. Right?
Yes, sir.
Everybody got that?
Yes, sir.
So we get 78 cubic meters. Okay? Alright? Okay with that?
Sir.
Alright? So now, next now it says that blocks X and Y in figure 5 are identical except for their temperatures. Then they say we need to explain the difference in the motion of the particles in block X compared with the motion of the particles in block Y. So what we can say for this? For block X, no, let's start there. Let's do X first. So for block X, what do we say?
Sir, the particles in block X would gain more kinetic energy, sir. So hence they would be moving faster with greater force and would collide more often into the container of the box, with the walls of the box.
Okay, cool. So as I mentioned, they will have a greater kinetic energy. But why we say they have greater kinetic energy?
They have a higher temperature than in the particles in block X have a higher temperature than particles in block Y.
Right. So because of the higher temperature, we will have more kinetic energy. Because remember, temperature is just a measure of the average kinetic energy. So we could say now that the particles in X, the particles move faster than those in Y, right? Next one now, for Y now, what we're going to say now, in this case, that so if Y is at a lower temperature, the particles we expect to move how? Slower, right? So the particles, right, move slower than those in X. Okay? All right? Good enough? Is this good enough?
Yes, sir.
All right? Now it says, in which direction would thermal energy be transferred? So what can we say?
Sir, south, that will be going down.
South, okay? All right? So in other words, it's going to be going from X to Y. Yes?
Yes, sir.
Because remember, the direction of net thermal energy transfer or net heat transfer is always from the hotter object to the colder object. So we're going to say that thermal energy.
That's what I said. This coming on the exam too.
It's possible to be there, right? I can't say. I'm saying it's a possibility. That's why we're going through questions like these. If I'd known what was coming exactly,
So that means we have.
Go ahead.
That means we are telling that fusion and everything too.
Negative. Right. I mean, you should know it, but based on what they say, it's not coming on the paper. It's likely not to be on the paper. Let me say that because I don't know what's coming on the paper, you know. But based off of what they submit, that's what we're using to guide our preparation. All right. So it's fair enough.
Yes, sir.
Okay. So thermal energy will be transferred from. Which one was the other one?
X to Y.
Sir,
X to Y. All right. Then now it says now we're to state the condition under which the transfer of thermal energy would cease.
sir, thermal energy would cease and both have the answer.
Okay. So this will occur, or this occurs, right, when, and they say the condition. So we want to tell them the name of the condition. So the condition, right, is referred to as thermal equilibrium, right, is achieved. And based on what you had said, Sarah, thermal equilibrium would be achieved when what?
Sir, when both boxes have the same temperature.
Right, when both objects, right, have same temperature. So we're gonna.
So sir, so what if I didn't state the condition? I'd get it wrong.
No, you wouldn't get it wrong.
Get it wrong?
You wouldn't get it wrong, because I mean it's. And you know, to be fair with this, the word not the question, because they said state the condition, right? The condition would be when both achieve the same temperature, right? They didn't explicitly say, okay, name the condition, right? And you would have to say, okay, thermal equilibrium. So, I mean, you wouldn't lose the mark, right? To be fair with the question, you wouldn't lose the mark. You would definitely be given your mark, all right? Okay?
Yes, sir.
Right? So let's continue now. So question 5 now says that complete table theory relates electrical circuit symbols to the names of electrical components. So this right here, what's this one? First one, what's it?
A switch?
This one?
No.
Sir,
Battery?
cell.
Battery. Right? We all agree to say it's a battery.
Yeah.
I read something else. Who was that person?
So,
Cell, right? So this is a cell because when we have this diagram right here, which shows a single positive and a single negative, this shows a cell, right? If it's multiple, it's going to be the battery. How we represent the symbol for a variable resistor?
a box with two lines
Box with two lines.
at the end.
Okay. That's it?
With an arrow going through it.
Right, with an arrow. Right? Because the variable resistor, so the arrow shows that the resistance it can be changed. Alright? This symbol right here, what's this?
Well,
Right? So this is our bulb. Okay? What about this one?
so the source.
Source. Okay? More specifically?
The power source.
Yes, power source, but a little more specific. Shanice? Shanice?
I don't know.
Right? We were talking about this the other day. What type of source is this?
So I don't want to say. I'm afraid I say something wrong.
No, say it, say it. I mean, this is the time where we're going to get things wrong and we'll correct it, if it is that we're unsure. So what do you say? Huh? This would be what? Alright, focus on this thing in the middle right here.
Sir, AC.
Right. AC source. Okay, I would say AC power source. Alright? Yes?
Sir, so power source is wrong?
No, that's not the correct because the power source, it could have a different power source, but specifically this is an AC because of this sinusoidal symbol. So yes, it is a power source, but we have to be specific, right? Just as how they ask for a variable resistor, if we had given this, it wouldn't be correct. Okay?
Yes, sir.
Right? So semiconductor diode, what's the symbol?
It's the triangle thing.
Triangle
The plus
thingy.
and negative.
Okay. Alright, the triangle that looks like this. So this is the symbol for a semiconductor diode. Now this one at the end, what's this?
Sir, fuse.
Fuse, absolutely. Right? So that's the fuse. Okay? Can move again?
So let me just take it on, please.
Quickly. Alright, let's move in the interest of time. I'll just make this available for you afterwards, alright?
Alright.
Okay. So this now says that figure 2 shows a circuit diagram, right? We have our circuit diagram. Now, let's say we're to state the formula which relates voltage V, current I, and resistance R. What's that formula?
V equal IR.
Right, V is equal to IR. So V,
Ohm's formula. Ohm's law.
right, so V is equal to IR for Ohm's law. Now, next one they said now we're to calculate the value of R2. So we want to find the value of R2, which is this resistor right here. So how we do that now? How we going to do that?
So,
Yes, how we going to do that? Yeah. All right, so what we say now? How we do this now? How we do this thing?
Sir, R equals V over I.
R is equal to V of I. Okay, all right, so let's write that down. All right, so we say R.
And then we make R the subject.
R is equal to V over I. All right, why would I have R being the subject? R is equal to V over I. Okay. What is V?
24.
24. Okay. But notice that this 24 volts, right, is what will be delivered to this entire circuit. And we're trying to find R2. So will this 24 volts go only to R2?
So why we couldn't use the formula RT is equals to 1 over R1 plus 1 over R2?
Okay, good question. When do we use this formula? When do we use this formula? And by the way, is it RT or 1 over RT?
RT.
No, 1 over RT. Right? 1 over RT.
Oh, because it's parallel circuit.
Right, we use this when do we use this?
To find out how much resistance calculate the amount of resistance.
In what type of circuit?
So not parallel?
Parallel, right? For a parallel circuit. But is this a parallel circuit?
So there's a series.
Right, so a series circuit. How do we find the total resistance in a series circuit?
Also, you have to use RT then, not a 1 over RT.
But RT is equal to what? What do we say?
So
R1 plus R2.
Okay, R1 plus R2 for series. Okay? But, I mean, what's the total resistance?
Yes, R1 is 4 ohms.
Hold on a second, hold on. Let's not rush.
then we can't know the total resistance because we don't know R2.
Right, we don't know the total resistance because we don't know R2. But consider this for a second. Right? We have 24 volts right here, and we have 2 amps flowing in the circuit. Now, that 2 amps flowing is due to what?
Current.
Yes, that's a current, but the 2 amps of current is due to what?
So R2?
Well, not just R2.
Or all of the resistance.
Right.
Total resistance.
Total resistance, R1 and R2. So therefore now, if we know that, okay, when we have 24 volts, a current flows of 2 amps, so this is the total, or the EMF of the source. This is the current flowing in the circuit, right? And this current flows in the circuit because of the total resistance, right? Which is due to R1 and R2. So therefore now, we can now consider this to help us to find out, okay, what's going to be the total resistance. So we're going to say that RT is going to be VT. We could say VT over IT. Could we say that? Could we say that?
Sir, I don't understand why you're saying that.
We're saying that because, all right, let me start right here. So we're saying that because the current flowing through the circuit is equal to the total voltage of the circuit, which is VT, right? So the total current is IT, which is this value right here. This current flows because of the voltage right here divided by the total resistance in the circuit, right? So we say RT. You with me? Say
Yes,
O.
sir.
Say
But
O.
we're using the T because our series.
No man, we're saying T because we want to indicate that it is total. Okay?
Oh, okay.
So the total current in the circuit is due to the total voltage of the circuit, or the total voltage of the source, divided by the total resistance of the entire circuit. Good?
Yes, sir.
When we rearrange, we get this value, right? We get this expression, RT is equal to VT over IT. Everybody good so far?
Yes, sir.
Yes, sir.
So VT then now is 24 volts divided by IT, which is 2 amperes. So we get a value of what?
12.
12 volts. Sorry, not 12 volts. 12 watt. Because the resistance we find says 12 watt.
Resistance.
12 ohms. 12 ohms. Unit is ohms, right? 12 ohms. Yes. So then, we know the total resistance. We know that it is 12, right? So now, from this now we can say, okay, 12 ohms must be equal to R1, which is 4 ohms, plus R2. So therefore now R2 will be equal to what?
12 minus 4 ohms.
Which is
8 ohms.
8
8.
ohms. Right? That makes sense?
Yes, sir.
So R2 is 8 ohms. So this is how we would go about working this one out. Okay? So that's our answer there for that one. Right? Then notice how we
Or
need.
sir,
Yes. Yes, sir?
sir, could you have just let the like, since RT would be the R1 plus R2 plus R3 equal VT over IT? You can
Repeat?
just set it to that. Sir, oh, no bother, sir, no bother. That's it. No bother. No bother.
Well, it's saying IT is equal to VT over R1.
I just realized. I realized I never use R3.
Okay. Okay.
So,
Yeah, true. True.
Right, yes, because notice, I mean, the switch is open, so R3 is not a part of the circuit. So that's something that, we have to consider in this case, right? Because we still need to know the total resistance. But again, this switch right here, it is open. So R3 is not connected in the circuit. So no current will flow right here. Okay?
Sorry, I'm recognizing 88 ohms, but it's the same thing for I.
Not hearing you, Shanice. You have a microphone covered up or something.
Right? Is it actually the same thing for the like R2?
What do you mean?
For R3.
I'm not hearing it.
R3 is the same 8 ohms.
Okay, right, yes. That's after the calculation, after we did the calculation. Right, but again, with this circuit right here, R3 is not yet a part of the circuit because the switch right here, it is open. Right?
sir, but isn't it connecting wire, sir? So if the switch open, wouldn't the rest of the resistance not work?
No man, because current will still have a path to flow. So if current flows through R1 right here, it's going to continue through R2. When it comes right here, it won't have any path to continue flowing, so it's going to be
With
blocked off.
R3.
So it's going to be blocked
Oh,
off.
it will have a part. Yeah.
Right, so it's going to continue through R2 and go around. You got that, Sarah?
Yes, sir.
Right? So as I said, this is not yet a part of the circuit. All right, any more questions?
No, sir.
Okay. All right. So next
So if
thing,
you wanted to find current,
repeat.
alright, see the formula for current.
Okay. So it says now, what is the reading on the voltmeter? So we want to know the reading on this voltmeter. So how we going to do that now? How we going to find the
So
reading?
24?
No, man, we can't just jump and set. Remember earlier, I said this 24 volts will not only go to this resistor. It will have to go to this one. Some of it has to go here. Because remember, we have a series circuit. And with a series circuit, the source voltage or the EMF of the source is always shared with the components. So this 24 volts is going to be shared, right? We don't know how. So that is why we need to find the voltmeter reading, which will give us the potential difference across R2. You with me?
So we had to find potential difference, which is P is equal to VI.
P is equal to VI. No, man, that's P is power.
Sorry.
Okay? So we need to find the potential difference across R2. Everybody okay with that? You guys have to talk to me now. Let me know what's
I
what.
think you need to go it over because I don't think we play.
But I need persons to tell me what's going on. I mean, you know?
Yes, sir, I get what you're saying, sir.
You get what we're saying? So again, the examiner says, where is it? What is the voltmeter reading? Now the voltmeter reading represents the potential difference across here, right? The potential difference across here. So what we need to say to ourselves now, okay, what formula we can use to find the potential difference across a resistor? What's the formula we can use to find the potential difference across a resistor?
V plus IR.
Right, from Ohm's law, V is equal to I R. Now in this case, what is I?
2, I think.
Huh? What's I? What's I? What know what is I? Or who is I? Huh? Anybody know what is I?
2 ampere?
2 amperes. But
Is it 2
what?
ampere?
Yes, why we say 2 amperes?
Because the theta is gonna have I. I is equals that.
But most
To say that with the
importantly,
current flowing.
most importantly, it is 2 amperes because we have a what type of circuit?
Series.
Series circuit. Once you have a series circuit, the current through all the components will be the same. So if we have 2 amperes flowing in the series circuit, 2 amperes flow through this, 2 amperes flow through this. So the current through R2 is in fact 2 amperes. What's the resistance of R2?
Sir, 8 ohms.
8 ohms, right? So this works out to be
16
unit
volts.
volts, right? 16 volts.
Voltage.
Okay, volts. Now, they're saying now that if switch S is closed, what would be the new reading on the ammeter? Right? So in other words, they want us to find, let's go back to the diagram. So when we close this switch right here, when we close this switch right here, we want to know what's going to be the current now flowing through this ammeter, which will represent the current flowing in the entire circuit. Okay? You with me?
Yes, sir.
So how we're going to do that? Can we start with a formula? What's the formula we're going to use to help us?
Sir, would you have to find the total resistance first?
Yes, you have to find the total resistance. But let's start with the formula that's going to help us to find the current first. And then we're going to build from there. What's the formula we're going to use?
V over R equal I.
Okay, so I equals V over R. Now, V is what? What's V? We need V,
24.
24, right? Which is for the entire circuit, so 24 volts. But R now is what we don't know, right? So we need to find the total resistance, okay? So we need to find the total resistance due to R1, R2, and R3, which is now part of our circuit, okay?
Yes, sir.
So what do we do now?
Sir, would it be that R1 and R2 is in a series while R3 is in a parallel?
Okay, but we need at least 2 resistors for us to say they are parallel. So which 2 resistors will be parallel? So again, just as we
So R2 and R3?
right, because watch this now. When the current, let's say the current leaves right here, it's going to flow through R1. Then when it reaches right here, what happened? Well, let me use it. When the current flows, let's say the current is going like this, right? When the current reaches at this point, what's going to happen?
So it's not split.
It's going to split, right? So some goes here and the rest goes there. So they're going to split. So once the current split, it simply means then that these two resistors are parallel to each other. Clear? Yes? No?
Yes, sir.
So if R2 and R3 are parallel, what we can do is we can first simplify, or in other words, find the equivalent resistance of these two resistors in parallel. So once we're dealing with resistors in parallel, we can say 1 over RT is equal to 1 over, let me just call this R2 and R3, 1 over R2 plus 1 over R3. And more appropriately, I want to say REQ for this one, because it's not really the total resistance, it's the equivalent resistance due to these two. So therefore now we're going to have 1.
Oh, sorry, no,
Okay, good.
oh, other one is the upright circuit, so that way it's parallel and it have a line. Oh, I know. So it's two circuits was connected to this.
No man, is one complete, one complete circuit now, when we close the switch right here. Okay? It's still one circuit.
But the little circuit is parallel.
No, it's not a circuit, it's just a section, right, with a switch and a resistor.
Section.
But when we close this now, we now create that two pathways for the current to flow.
Okay.
Right? So R2 was 8, so we have 8 right there, plus 1 over R3. R3 was also 8. What's the LCM right here? What number can both?
Sure, 8.
Right, 8. Right? So 8 into 8 goes 1, so we have 1 plus 1. Right? So we have 1 upon R EQ is equal to, this is what, like 2 over 8. So we reciprocate both, we're going to get REQ is equal to 4 ohms. Is that so?
Yes.
Right? So therefore now, these two resistors, R2 and R3, we can just replace them with one single resistor, right? One single resistor having this resistance, 4 ohms. Okay? So therefore now, if we quickly sketch it out, our circuit is going to look something like this. That's R1 right there. Right? And then we're going to have one resistor right here, which represents R2 and R3, or ammeter here. Right? Something like this. Okay? So this is R1 and this is REQ. See that now?
So, but if that's the like just sketch a circuit, you could sketch it like any one of these.
No, it all depends on what they're asking you. If they say sketch a circuit with two resistors in series, then you sketch this one. Right? If they say sketch a circuit with two resistors in parallel, it's going to look a little different. So you have to be specific in terms of what the examiner is asking. Alright? 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 So now we have, this is 4 ohms. This is 4 ohms right here. But these two resistors now, they are in what type of configuration? They're in what type of configuration? Let's go. What type of configuration?
So it's on the same side. Both of them on the same side.
Sir, the question there.
Yes, these two resistors are in what type of configuration? Are they in series or are they in parallel?
Series?
Series, right? Because again, in this case, current only has a single path. So if they're in series, we can say that RT now, which is due to these two resistors in series, is simply R1 plus REQ. So this is
8 ohms.
right. So 4 ohms plus 4 ohms will give you 8 ohms.
8 ohm.
So now we can go here now and we can say, all right, this is 8 ohms. So therefore, now if that's the case, we will have 24 volts divided by 8 ohms, and this is what value?
Ohm. 3
What is it? Michaela?
Say 3 amperes.
Right, 3 amperes. Okay. Michaela?
Yes, sir.
Is you following?
Yes, sir.
Okay. Any question?
Yes, sir.
All right. So that's that question. Kiara?
Yes, sir.
Yes, all is well?
Yes, sir.
All right, so let's go now. This is the last question. So let's see if we can do 10 minutes and finish it. So copy figure 3 and draw the ray diagram. Sorry. Copy figure 3 and draw the ray shown as it emerges on the other side of the lens and its relation to the focus. Show the principal axis and focal length. So this is a lens question right here. Right? What type of lens we have in front of us?
Concave.
Concave, right? And we say concave because
The middle is smaller than the
right? So it's thicker at the ends than in the middle, so it's a concave lens. So now, in this case, now they want us to show the principal axis and the focal length and show the path of this ray. So let us say we first draw the principal axis, which will go straight through like that. Sorry, let me try to keep this in the middle a bit. So we have our principal axis, let us say like so. So that's our principal axis, right? Now, somewhere on the principal axis, we're going to have our focus, our principal focus. So let me just put that in. So this is our principal focus, let us say at this point right here, right? Now, let's say we need to show the focal length. What's the focal length? What's the focal length? What is the focal length?
The distance
Yeah.
center of the lens to the principal focus.
Right, so the distance from the center of the lens to the principal focus. So this distance right here would be our focal length. So that's the focal length. But we also need to show the path of this ray. So once this ray passes through the lens, what will happen to it?
It will spread out.
It's going to spread out, right? So it's going to continue like so, right? And go like this, okay? After it passes through the lens. Now we need to show the relationship between this ray and our focus, in this case, which is our principal focus. So what we can do now is we can now show that, okay, because this is diverging, right? It must be coming from a common point. So we can show that the common point will be our principal focus. So we can just trace this backward, right? Like that. So this will be our diagram. Cool?
Yes, sir.
All right, so we can move again.
Yes, sir.
All right, so next one now, it says that write in words
sir.
or symbols the formula for the magnification of an object. All right, what do we write right here?
M is equal to V over U.
M is equal to V over U. Where M is our magnification, V is what?
M is equals to image distance over object distance.
Right, so the image distance over the object distance, or we could use what else?
Image height over object height.
Right, image height over the object height, right? So M is equal to V over U. Next here now says that an object AB is placed 20 centimeters in front of a converging lens of focal length f, which is 10 centimeters as seen in figure 4. Now it says now we're to calculate the position of the image formed and state on what side of the lens it is located. Walk us through this now, what we do?
F is equals to 1 over u plus 1 over v.
Repeat. Repeat for
1
me.
over f is equals to 1 over u plus 1 over v.
Okay.
1 over u plus 1 over v.
All right. Everybody agree with this?
Yes, sir.
Now we're trying to find v, which is our image distance. So we say, because the position of the image represents the image distance. So the position of the image represents the image distance measured from the lens. So therefore now, we're going to say, all right, 1 over v will be equal to 1 over f minus 1 over u. Because we just minus 1 over u from both sides. So we get 1 over f. What was f again?
10.
10, right? Right? Minus 1 over u, and u is?
20.
20, right? So now LCM of this would be 20, right? So 20, 10 into 20 goes 2 times. So we have 2 ones, 2 minus 20 into that goes 1 time. So 1 times 1 is 1. So therefore now we're going to have that 1 upon v is equal to 2 minus 1, which is 1 over 20. So therefore v now is equal to
20 over 1.
right, which is 20
Centimeters.
centimeters. All right. So that's the position of the image. And they say what side of the lens. So what side of the lens will the image be located?
The right side.
Right side, right? So if the object is on this side, it's going to be on the right side, which is on the opposite side. So we're going to say that the image is on the opposite side of the lens. Right? Good? Now, this thing says we're to calculate the magnification. So we know the magnification formula, so we can say M is V over U. V is what we just calculated, which is 20 centimeters, and U was what?
20.
Right, 20 centimeters. So therefore, this works out to be
1
what?
centimeter.
1 centimeter.
1 centimeter.
Everybody agree?
Shit, just be wrong.
Alright, because remember, these
Yes,
two
sir.
cancel.
No,
So we have no unit for the magnification.
oh yeah.
Right? Next one now says that is the image formed real or virtual?
Sir, real.
Why real? Why real?
Sir, it's a real image because when the image is greater than the focal length, because the image is greater than the focal length.
The image or the object?
So is it that?
Has to be the object. Right? Has to be the object. So once the object is at a distance greater than the focal length, you always get a real image. And also, once the
Object up.
hold on a second. Alright, I'll allow you to mention what you have to say. But what we're saying is that once the object distance is greater than the focal length, you will always get a real image. Also, once the image is located on the opposite side of the lens, it's always real. Okay? Now, in this case, we're not able to see this, but once the image is inverted, it is always real. Okay? So if I sketch our diagram,
Yes, sir.
right, we would see that it's going to be inverted, which is, therefore, it's going to be real. All right, so that's that. So you were saying now, Shanice?
That one was going to see if the object is inverted.
Okay, perfect, perfect. All right, so have any more thing on any questions on this?
No, sir.
All right, everybody able to
No, sir.
get an appreciation for these questions now?
Yes, sir.
Okay, go on.
Sir?
Yes, you able to appreciate these questions now?
Yes, sir.
Okay, so we need to get access to the solutions of this, the written solution, as we did a while ago.
Yes. That's
Okay. All right, so that's that then. That's it. All right. Any questions before we go?
so you could just explain the virtual image more.
Right. So
It says if it's upright.
right. So a virtual image is always upright. Right. A virtual image is always upright. Now, a virtual image is going to be on the same side as the object, right? And also with a virtual image, it is not able to be projected on a screen. And by it being virtual, it simply means that light rays are not actually coming from it. And when we draw a ray diagram, we're always going to show a virtual image using broken lines. Okay? And the real image is always seen using solid lines. Okay?
Yes.
All right, so